Do you know you can pretty much design any beam if you know how to find out its internal forces such as axial forces, shear force, and bending moments. In today's lecture, I will teach you step-by-step process in S-frame, which is structure analysis and design software, how to analyze a beam. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. In this tutorial, I will show you how to model a simply supported beam with a distributed load and a point load in S-frame. First, the problem description. This is a simply supported beam where you can see a beam with length L and UDL applied. UDL is uniformly distributed load, which is W. And here we have a central point load. The beam is simply supported, which means that the left end is a pin support, right end is a roller support. A pin support has two reactions, vertical and horizontal, and a roller support has one reaction, only vertical. This is the actual problem which I will solve in S-frame. A 10 kilonewton per meter load is applied over 5 meter span. 50 kilonewton load is applied over 5 meter span. Note that the total load is same in both beams. Here 10 times 5 you will get total load. Here we have 50 kilonewtons. The total load is the same, but will bending moment and shear force be the same? Let us see. Let us find out what is bending moment and shear force in a beam with distributed loading. Let's draw these lines. So first, the shear force diagram. Shear force will be equal to total load divided by 2, which is WL over 2. Because this is a distributed load, the shear force is going to be 0 at the center. It will go down again, then we will have minus WL over 2. And finally, it will reach to 0 shear force. Bending moment, we will have maximum bending moment as WL square over 8, where W is the load, L is the span, and 8 comes from the formula. For point load, the shear will be total load divided by 2, and there is no load between left point and the central point, so it will be a straight line, and then it will directly come down at point P. And again, there is no loading between central point and the right point, so there will be P by 2. And then we can shade it to make it beautiful. Let's see how we can find out bending moment. Bending moment will have a triangular shape. The bending moment will be equal to PL over 4. Note the difference between bending moment diagram. In case of UDL, uniformly distributed load, we have a 2-degree curve. In case of a point load, we have a straight line. Now what happens if I have a 10 kilonewton load over 5 meter span? The shear force will be equal to 10 times 5 divided by 2. I get 25 kilonewton. It will continue to the right side, and I will have 25 kilonewton at the right side as well. And then you can shade this diagram to make it look pretty. Bending, on the other hand, will have WL square over 8. W is 10, L is 5. We get 31.25. In case of point load, central point load, we have shear force as P over 2. P is 50, and it will continue to the central point. Then it will come down. We will have negative 25 at the right side. This is how we draw the shear force diagram for a central point load. Bending moment, PL over 4. P is 50, L is 5. Divided by 4, we get 62.4. Note the difference. We get as much as double the bending moment in case of a central point load. And the reason is that because the load is going to be concentrated at one point, and this will induce quite a lot of moment in the system. By all means, try to distribute load on beams that will have gradual bending in beams. When you start S-frame, you will get this dialog box where you will start with two-dimensional mode. Click on 2D. It will ask you for the name. I will say SS beams. Next, it will ask you for the unit. I will accept the default units. Next. These are the code provisions, but I'm not concerned with code at the moment. I will start from scratch. So open a blank document and then finish. Here, the first thing I want to do is I want to show the grid. So for showing the grid, you will click here, edit grids. Here you will display equal spacing 1 meter grid, which means that there will be 10 grids in positive x direction, 10 grids in negative x direction, and same is the case with y grids. Make sure you click on display grid, lock grid to joints, and lock guide. If you click OK, you'll be able to see this grid, but you can't see it fully. So to see it fully, simply click on here, zoom to grid extents. In that way, you'll be able to see full grid. These are the 7 steps which I'm going to follow to model these beams in S-frame. First, geometry. Second, boundary conditions and member releases. Here, I don't need member releases. Material, section definition and assignment, loading, analysis. And 7 is the post-processing, means that how do we view the results? First step is the geometry. So let us define geometry. So if you click on geometry and click on member definition tool, there are 2 options now. One is 2 joints, other is 1 joint. I will first create members with 2 joints and then I'll show you how to do it with 1 joint. So starting from here, I will click anywhere and then I will count to 5. And then for the second beam, again, I will click here, then I will count to 5. If I wanted, I can do it with 1 joint as well. So with 1 joint, I want member to go in positive x direction and member length is 5. If I click over here, it will create a member. If I click over here, it will create a 5 meter member. The next step is to define boundary conditions. So if you click on here, this is the support tool. I want to define a pin joint at left, which means that it cannot translate in vertical direction, it cannot translate in horizontal direction. So it is free to rotate. So then clicking on here, creating a box, I have these supports. On the right side, I want to define a roller support. So click here and create a box. In that way, you'll be able to define a roller support. The next thing for me is to define the material. I'll click on material properties. Here I will define steel material for beam with uniformly distributed load, and I will define concrete material for beam with point load. So steel Eurocode 3. I will click a box over here. Then I will define concrete number 7 for beam with point loads. Then I will define a section. The section properties tool. Right click on that. Click on steel, and here I want to define I section. So clicking anywhere, I will define this I section, and for concrete, I will simply create a shape. I want to create a new shape. So I want to create 200 wide by 500 deep. And then I will choose this rectangle. Here I will specify 200, click OK, 200 times 500, and then I will add this. And then simply close this. Actually, I should have changed the colors. So let's change yellow color to the steel beam and blue color to the concrete beam. So right side, I want to define the concrete beam for the point loads. Once the sections have been defined, the next step is loading. Let's go into loading. And then here, I want to define a distributed load. So click on global load, full uniform, y direction, and it will be -10, which means that it will define a downward load. And then I want to define a concentrated load. So click on concentrated load, point load, y direction. I want to define -50. My location is going to be 0.5. 0.5 means that it is at the center. 0.25 means that it is at the first quarter point. 0.75 means it is at the third quarter point. So I will say 0.5. And then simply I'll click here. You can see that the central point load has been applied. Once the loading is applied, then this is now ready for analysis. So go to run analysis.
and then linear analysis. Simply, I will save the file. A clean solution. Last step is post-processing or viewing the results. So for this one, you will go to graphical, and then firstly, you will see the deflection. So here it's showing you deflection. I want to see deflection in Y direction. Here it's not showing me the values. So I will go to settings, diagrams, and here display values on diagrams. Here I will invert the diagrams as well, because I want to see the bending on the sagging side. In North America, they view bending on the hogging side. And then normally I specify maximum projected length as 10. If you double click on this, you'll be able to see maximum deflection, which is 2.19. Here, the maximum deflection is 10.8. And this was quite obvious because the material is concrete for point loads, so it will deflect more. And then I want to see the reactions. Reactions are similar to what we obtained from manual analysis. The axial force, there's no axial force. This is horizontal beam. Shear force, you can see it exactly resembles what we got from the theoretical background, 25 and 25. And bending, you can't see the maximum value here, so you will double click on that. 31.25, again similar to theoretical background. Here you can increase the stations to make it more gradual. So here it looks like what we drew in theoretical slides. Again, if you want to see bending over here, you'll be able to see this bending, 62.5, which is double than UDL.